So, let us continue now. In the previous two videos, we looked at the first and the second Sylow theorems. The first one said that a group finite group G has a Sylow P subgroup if P divides the order of the group. Second Sylow theorem said that any two Sylow P subgroups are conjugate. The third Sylow theorem says something about the number of Sylow P subgroups. So, let us prove this. Let us first state this. So, let G be a finite group. The setup is as in the first two Sylow theorems. So, let G be a finite group and let P be a prime that divides order of G. So, we write order of G as P power E m, where P does not divide m. Okay. So, as always, let small s be the number of Sylow P subgroups. So, as I said, the third Sylow theorem is a statement about the number of Sylow P subgroups. Let us call it S. Remember, S is at least 1 by the first Sylow theorem. Then the third Sylow theorem says two things: S divides M. Okay. So, remember M is the factor of in the order of the group which does not contain any P after removing all the factors, largest power of P that is available. So, S divides M, and 2 S is of the form A P plus 1 for some A in natural numbers. Okay. So, that means when you divide S by P, you have remainder 1. So, let us go ahead and prove this. Proof is again a clever use of group actions, as the first two Sylow theorems were. Here also we cleverly use a group action on a suitable subset. So, here I am going to consider the set, the useful set here is capital S is the set of all Sylow P subgroups. So, this is H is a subgroup of G and the order of H is P power E, that is the set S. Now, we want to consider a G action on S. So, remember G acts by two things on itself or subsets, either by left multiplication or by conjugation. Here if you take left multiplication, it will not give you an action. Why? Remember, S is not just a subsets, S is not the set of subsets, it is a set of groups, it is a set of subgroups. So, if you take left multiplication, you are no longer going to be in the set, because if you multiply a subgroup by an element on the left, you will have a subset, not necessarily a subgroup. So, if you consider the action of G on S by left multiplication, it will not give you an action, because our set now consists of subgroups. So, we are going to consider the action by conjugation. Remember, as I said in the previous video, conjugation preserves this set. So, in other words, if H is in S, then G and G is in G, GH is also GH by definition is GH G inverse. So, here it is not the left multiplication, it is the group action G dot H is also in S because GH inverse is a subgroup and its order is also P power E. So, it is an action. So, now this is the goal for us. Now, by the second Sylow theorem, so first of all let us fix some element of H S. So, let H be in S. So, that is H is a Sylow P subgroup of G. What is the orbit of S? Oh, sorry, orbit of H. What is the orbit of H under this action? Remember, the proof in this case completely depends on the action of the group G on this set S by conjugation. What is the orbit of H? It is all G H G inverse as G where is in the group G H G inverse. Now, remember G H G inverse are all Sylow P subgroups, that is okay, but by the second Sylow theorem this is all of S. Correct? Because any two Sylow P subgroups are conjugate. So, you take any element of S, namely a Sylow P subgroup, it is conjugate to H, because any two Sylow P subgroups are conjugate by second Sylow theorem. So, there will be a suitable G such that G H G inverse is that Sylow P subgroup. So, the orbit of H is all of S. What is the stabilizer of S? H. Stabilizer of H is all group elements such that G H G inverse is H. Under the action you must get back H. This is what we call the normalizer. If you recall from one of the earlier videos, this is the normalizer of H. So, let us denote this by N of H, and for simplicity I am just going to call it N. Okay. So, now the counting formula gives me the following. Counting formula applied to this particular G action on S and for the element H. It says that cardinality of G is equal to cardinality of stabilizer of H times the orbit of H. This is the counting formula. This is p power e times m. This is equal to, what is the stabilizer of H? This is order of n. N is my notation for the normalizer, and orbit of H is S, right. Orbit of H by the second Sylow theorem is all of S. So, N P E m is equal to capital N times capital S. So, capital N order capital N times, remember our notation was number of Sylow P subgroups was used called S, right, in the definition, in the statement of the theorem. Small s denotes the number of Sylow P subgroups. Capital S is the set of Sylow P subgroups. So, order of S is small s. So, p power e m is S times order of n. Now, what we have is the following. Normalizer of a subgroup H will always contain the subgroup. So, we have this, because remember normalizer is all elements such that G H G inverse is equal to H. If some element is already in capital H, certainly it will be contained in the normalizer. So, we have this. Then I claim, so we have the index of n in G divides the index of G in H, H in G. Why is this? I will quickly tell you why. What we have is the counting formula for the subgroup of a group tells me that, right, this is one of the original counting formulas. Order of the group is the index times order of the subgroup. But remember, this is also equal to the index of n in G times order of n. I am applying the counting formula first to H and then to n. But since H is in n, Lagrange's theorem says what? Lagrange's theorem says that order of a subgroup divides order of the group. So, order of H divides order of n. So, we can write order of H times some let us say L is order of n for some L in natural numbers, positive integer. So, now let us recall this. So, G order of G is order of G index of H times order of H, which is index of G n times order of n, but order of n is order of, so I am going to rewrite this as index of n, and instead of n, order of n, I am going to use this order of h times L. So, now I will look at this term and this term and cancel h, order of h. So, order of index of h is equal to index of n times L. So, index of n divides index of h. Okay. Index of n divides index of h. Now, let us look at the counting formula that we had earlier. What is the index of n? So, I want to understand. So, by the counting formula, we have order of g is equal to s times order of n, right. So, this implies s is equal to order of g divided by order of n, which is index of n. But what I have just concluded is or index of n. So, is that clear? We proved earlier that order of g is equal to small s times order of n. So, small s is order of g divided by order of n, which is by definition the index of n, not by definition, but by the counting formula is index of n. But we know that index of n divides index of h. And what is the index of h? This in turn is order of g divided by order of h, but h is, remember, a Sylow P subgroup. So, this is P m by P e, this is m. Okay. So, s is the index of n. So, s divides m, and I think this gives one, I called it 1 of the theorem. Remember, the statement of the Sylow theorem is that if you call small s the number of Sylow P subgroups, it divides m and it is of the form a p plus 1. So, I have just proved the first part of it, right. This gives the first statement of the theorem. To prove the second theorem, second part, to prove 2, I am going to consider a different action by a different group. To prove 2, we consider a different action. So, here I want to consider, we look at, so earlier I looked at the action of the group G on the set of all Sylow P subgroups, that gave me the statement 1. To prove statement 2, I will look at the action of H H is a, okay. So, we actually fix, so fix a Sylow P subgroup, call it H, and we look at the action of H on the same set as above. So, S being all Sylow P subgroups of G, right. So, as in the previous state part 1 of this theorem, S was the same set, I am only changing the set, the group which is acting. I do not consider the action of G, all of G, I only consider the action of the group H. So, Sylow P subgroups, the set remains the same, and I am going to call this set H. See, H is an element of this, right. So, H1 is called, I am just going to take H as H1, H2, H3, and remember there are S of them. Small s is the number of elements of capital S. So, we look at H acts on S, H action on S by conjugation. So, only difference from the first part is, instead of looking at the action of G on S by conjugation, we look at the action of H on S by conjugation. Okay. So, now what is the, so I am going to figure out what is the orbit of H. First I am going to understand what is the orbit of H. what is the orbit of H? So, orbit of H, so ORB of H is all G H G inverse, but now where is G? Because, so maybe I should call what is the H orbit of H. Remember, I am no longer interested in the action of G. What happens outside H is of no concern for me. I am only interested in the H orbit of H. What is H orbit of H? It is all groups of the form G H G inverse where G is in H, but this is exactly H, right, because if G is in H, G H G inverse is H. So, orbit of H is just the singleton H. Now, choose some, let any I be any number bigger than 1. What is the orbit of H I is what I want to think about. Now, and for that I will suppose that H I is an H orbit of H, of S rather. Remember, I am looking at capital H acting on capital S by conjugation. Suppose that some Sylow P subgroup different from H, so I is greater than 1, different from H, let us say H I forms an orbit by itself. What can we say about H I is what I want to understand. But if H I is an orbit by itself, then what we have is H times H I times H inverse is equal to H I for all H, right. This is the meaning of capital H I being an H orbit, because H orbit of H I is all elements like this, all subgroups like this, but it is just H I. The singleton H I is an H orbit, that means H times small h times H I times small h inverse is equal to H I for every H in H. That means small h is in normalizer of H I for all I, right. Small h is a normalizer of H I for all I, because what is a normalizer? Recall, I am going to call it N I, which is a normalizer of H I, is by definition all G in G such that G H I G inverse is H I. If you go back and see in the earlier part of the video, normalizer was defined to be this. Now, if H times H I times H inverse is H I, then H belongs to the normalizer. So, H for small, for every, sorry, it is for all I H in capital H. That means capital H is in normalizer of H I. So, capital H is in N I. So, now we have two things. So, we have H and H I are both subgroups of N I, right, because I concluded here that H is in N I and I definitely know that H I is in N I, that is not a problem. H I is in N I, H is also in N I. So, they are both subgroups of N I. Moreover, H and H I are in fact Sylow P subgroups of N I. Why is that? What are Sylow P subgroups of N I? You look at the order of N I, you look at the largest power of P that appears in it, and you look at those subgroups of that order. Remember, N I is a subgroup of N. So, order of N I divides order of N. So, the largest power of P that appears in N I cannot be more than E, which is the, so in fact what we have is also some N I is P E M prime, because remember what we have is H I is contained in N I contained in G. So, this has order HI has order PE, G has order PEM. So, order of Ni must be divisible by Pi by Lagrange's theorem, and in turn it must divide PEM. So, it must be some M prime, right. So, Sylow P subgroups of Ni are also subgroups of order P power I. H and Hi, remember, are subgroups of order P power I. They are both subgroups of Ni and they both have order P power I. So, they are both Sylow P subgroups of Ni. So, by the second Sylow theorem, so just to repeat, the largest power of P that appears in Ni is also P power E. So, Sylow P subgroups of Ni are subgroups of order P power I, and we have shown, we know that H and Hi are both subgroups of N and both have order P power, they are both subgroups of Ni and both have order P power E. So, they are both Sylow P subgroups of Ni. Now, what does the Sylow second theorem say? It says that any two Sylow subgroups are conjugate. So, H and Hi are conjugate in Ni. So, here I am only focused on applying the theorems to Ni, not to G. So, apply the second Sylow theorem to Ni. Ni is a finite group, H and Hi are subgroups of Ni which are both Sylow P subgroups. So, they are conjugate in Ni, that is, there exists G in Ni such that G H I G inverse is H, right. This is the meaning of being conjugate. But if G is in Ni, recall what is Ni? Ni is the elements G such that G H I G inverse is equal to Hi. This means G H G inverse, G H I G inverse is Hi, but this is also at the same time equal to H, because G H I G inverse is H. That is the assumption, that is the consequence of the second Sylow theorem, because they are conjugate, but G being in Ni forces G H I G inverse to be Hi. This is the definition of Ni. That means H is equal to Hi. So, the upshot of all this is, if Hi is an orbit, he is an H orbit in S, then Hi equal to H. Okay. So, if Hi is an N orbit, Hi is an H orbit of S, then it is H. What we have shown is H is an orbit by itself, that is okay, but if Hi is an orbit by itself, we must have that Hi is equal to H. So, it is the only singleton orbit of S. So, written differently, H is the only singleton orbit in S. Singleton orbit means an orbit consisting of a single element. It is the only singleton orbit of S. Now, consider orbit decomposition of S. So, we have the size of S, which remember was denoted by small s, is order of O1 plus order of O2 plus order of OK, and let us assume that order of O1, O1 is orbit of H. H was the fixed thing that we had dealt with. Okay. So, that is H. So, order of O1 is 1 plus order of O2 plus order of OK. So, here of course, I am looking at H orbit decomposition, and by what we have done above, by the above argument, order of OI is at least 2 for all I from 2 to k, right. So, every other orbit has at least 2 elements, because if it has only one element, it must be H. So, it has to, and that we have already accounted for. So, they are all at least 2. But now apply counting formula. What do we get in the counting formula? Here we are looking at the odd H action. So let us say OI is the orbit of HI. So if that applied counting formula applied to that says order of H is stabilizer of OI, stabilizer of HI times the size of OI. But what is the order of H? H is a Sylow P subgroup. So order of H is PE. So this means order of OI divides P. This is great. Order of OI divides P, because P power E is stabilizer of HI times order of OI. So order of OI divides P, but for I at least 2 we have two facts: order of P OI is at least 2 by this argument, and it also divides P. Okay, so it can't be 1. So they are all at least 2. So now let us look at the orbit decomposition of S, and I am going to write it like this: small s is the order of S, which is O1 plus O2 plus OK, but we agreed to that order of O1 is 1 plus order of O2 is something times P, right, something times. So let us say order of OI is P times, let us say AI, right, AI is at least 1. So it is P times A2, P times A3. So order of O3 is P times A3, order of AK is P times AK. So 1 time plus P times A2 plus A3 plus AK, and you call this A. This is exactly the statement that we made. This gives 2. So the proof is complete, right. So we have shown that the number of Sylow P subgroups when you divide by P leaves a remainder of 1. So let us quickly recap this. The argument was, we look at we fix a Sylow P subgroup. So let us see where we started with this. So we fix a Sylow P subgroup and then look at the action of that Sylow P subgroup on the collection of all Sylow P subgroups by conjugation, and after some work we concluded that the only singleton orbit is H itself. Any other orbit must contain at least 2 elements. So the orbit decomposition looks like this: S equals 1 plus the remaining orbits, but the remaining orbits must divide P because of the counting formula. So all the remaining terms are divisible by P and 1 is left. So S itself must be of the form 1 plus AP. Okay. So let us again look at the example of S3 with that we have seen before. So here of course order of S3 is 6, which is 2 times 3. So the number of, let us denote by S2 the number of Sylow 2 groups, subgroups, and S3 is the number of Sylow 3 subgroups. The third Sylow theorem says so let us first do S2. So S2 divides 3 and S2 is 1 plus 3A or 1 plus 2A, right. But and what is S2? So as third Sylow theorem says this, but we know what is S2. What is S2? We already seen, right. There are 3 Sylow 2 subgroups. That does 3 satisfy this? Yes, of course it does, because 3 divides 3 and 3 is of the form 1 plus 2A. What does third Sylow theorem say about S3? We know of course we know S3 is 1. So, let us see if that is confirmed by Sylow theorem, third Sylow theorem. S3 should be a divisor of 2 and S3 must also be 1 plus 3a. So, 1 satisfies this. Correct, because 1 divides 2 and 1 is of the form 3a, 1 plus 3a. Okay. So, this says that this just confirms what Sylow theorem says, but I want to stress one fact here. Sylow theorem does not tell you exactly what the number of Sylow p subgroups is. Okay. It only gives you a range of possibilities. You have to further investigate the group to determine which possibility occurs. See, as in this example, before you knew this, suppose you did not know this, we can say that even if we did not know anything about S3, we can say S3 must be 1. Why is that? Because S3 divides 2, that leaves only 2 possibilities, it is either 1 or 2, right, but it also at the same time must be of the form 1 plus 3a, but 2 is not of the form 1 plus 3a. So, we can say S3 must be 1. This immediately no matter what the group is, even if you did not know that it is S3, S3 must be 2. On the other hand, S2 can be 1 or 3. Why is that? Because remember the conditions are S2 divides 3 and S2 is 1 plus 2a. Certainly 1 has these properties, because 1 divides 3 and 1 is of the form 1 plus 2 times 0, and 3 also has this property, 3 divides 3 and 3 is of the form 1 plus 2 times 1. So, Sylow theorem only says that S2 can be either 1 or 3, and in the example of the symmetric group, the option 3 is achieved. Of course, my notation is confusing here because the group and also S3, so I hope you do not get too confused about this. So, if the group is S3, then S2 is 3. On the other hand, let us take the group to be, if we take the group to be Z mod 6Z, this is also a group of order 6, then S2 is actually 1. This is an exercise for you. Z mod 6Z has exactly 1 Sylow 2 subgroup. Okay. So, in this case S2 equal to 1 is achieved. So, just to recap, Sylow theorem is not a conclusive answer to, third Sylow theorem is not a conclusive answer to the question of how many Sylow p subgroups exist, because it only gives you a range, as this example of order 6 suggests. Sometimes that range contains only one element, like in this case. If you have a group of order 6, we know that there must be only one Sylow 3 subgroup, that we can say, because that number has to divide 2 and at the same time be of the form 1 plus 3a. On the other hand, when you look at Sylow 2 subgroups, they are either 1 or 3, and as you can see in these two examples, both options are achieved. So, the Sylow third Sylow theorem is not very precise, it gives you a range of possibilities. Sometimes that range is very small, in fact it can be even one possibility. Sometimes you can further study the group to eliminate some possibilities, but as it is, third Sylow theorem is very useful. So, I will stop the video here. In the next video, I will look at some applications of Sylow theorems and solve some problems. Thank you.